Welcome to Signaling Basics for Model Railroaders. I'm Burr Stewart, and this is a brief clinic on what I've learned so far about how you might consider starting to use LCC for making a signaling system for your railroad. I've only just begun to learn, so this is just a status update. First of all, what's the problem? Why do you need signals? I have a large operating HO layout with no signals, just this imitation signal in the upper right-hand corner. And during operating sessions, things can get kind of crazy. Despite all of these aids, such as phones between dispatchers and circuit breakers, closed circuit TV showing where the trains are in the staging yards, and a dispatcher's panel, the need is still clear. We have accidents, we forget to put down the bridge, and if only this signal could light, we would be able to keep the train out of the yard. In this example, we have some friends from Vancouver, British Columbia that are operating on the layout, and we weren't able to prevent the Northern Pacific train on the left from coming in and clogging up the yard, causing Anita to have to bring her F units there across a crossover in order to get through town. But the worst problem on my layout is a Y called Delta Y, where trains from the north, the east, and the south all come together. It would be really great for me to be able to have a signal to keep them out of the Y until their turn has come. So the solution is an operating signal system. How hard can it be? Seth Newman has done it. Tony Keister has done it. Dave Abeles has done it. And he's even written a book about it. So how hard can it be? Well, in your mind, it can be pretty hard. The universal storyline plot, all the way from the original stories written down thousands of years ago, all go like this. Something needs to change, and you overcome your fear of change. You dive down and slay the dragon and emerge victorious. Now, in my case, the dragon is getting a signaling system working. And where I am is I've just learned enough to overcome my fear, and I haven't quite dipped my toe in the water to actually start building the circuits. Most of what I know came from these two books. Dave Abeles just recently published a book on his fabulous signal system in New Jersey, and Dana Zimmerly has written a nice book on layout command control. I recommend both of these books, and I'll give you a summary of what I've learned from them so far. First section of this talk is what to illuminate with a signal. You could have turnout position indicators, train order signals, grade crossings, junctions, automatic block systems, centralized traffic control, and structure lighting. I'm just going to focus on Delta Y, which is a junction, and just start and see if I can get that done. Now here's a map of the area around Delta Y, and I started thinking, well, what are all the signals that I could use to control that traffic? I came up with an enormous list of signals. So I thought, well, this is way too ambitious a project to start with. How can I simplify this? So I cut all that back and said, let's just control the trains in Delta Y. I still have a ridiculous number of signals. So then I thought, let's really get real here. All I need is a two-head signal controlling each of the three switches going into the Y. Since I want to have red, yellow, and green in both the upper and lower section of each signal head, that adds up to 3 times 6, or 18 LEDs, and I have to figure out how to light up. That seems doable. One thing I want to mention is the track heading towards the south, or coming from the south, is north-facing. So is that signal the north signal or the south signal? Now, I'm going to call it the south signal, but I just pointed this out to you because it could be very confusing fast if you don't decide how you're going to standardize the names you use for the different signals. So that's really lesson number 1. Now, the next section is, what are the electronic components involved in a signaling system? They're light-emitting diodes, or LEDs. They're resistors and diodes. power supplies, wire, train detection, which can be several kinds, and turnout position indicators and actuators, which can be several kinds. This is a picture of a signal head that I got from Seth Newman's company. It only costs about $1.25, and it plugs into a little socket there, and all these components are very easy to solder and make. And I thought this would be a great way to get started. I've only got to have 6 of these heads, and I've got my 18 LEDs. For $1.25 per signal, that's doable. But then I found out that those sockets you plug into called DuPont connectors. So I went and spent $12.50 on a package of those so that I'd be able to set up the sockets I need. And to do the wiring and sockets and everything, you need some specialized tools. And I ended up spending almost $125 on these 4 specialized pliers, which really cracked me up. Because here I am saying I can save money on signals, but by the time I get all of the tool infrastructure in place, look at the money we're up to. Of course, that doesn't include the electronics that's driving the LEDs. This is just getting the LEDs in place. Of course, you can buy this wire pre-made so you don't have to use the tools, but I like to play with tools. And when you buy them, they may not be the way you want them. There's the male-female problem, which is which wires plug into which sockets. And that can be pretty complicated too. So if you can make your own male and female connectors, that makes things a little easier. But seriously, who doesn't love playing with new tools? And how about this? The new soldering iron. What I like about this soldering iron is these various tip sizes are really handy for something as specialized as those little signal boards that I showed you. What I found in reading these books is there are 2 important things that people assume you know that it took me a while to make sure I was correct about. One is that LEDs only work one way. They have a positive negative side, sometimes called a cathode for negative and anode for the positive. And since the LEDs only use around 3 volts, there have to be resistors in series with the LEDs to cut them down from the more typical 5-volt power supplies or electronic circuits. And it turns out the electronic circuits tend to have off equals 5 volts and on equals 0 volts, or the other way around. They will, in the books, sometimes refer to the logic level without saying that's 5 volts. So the bottom line is you have to really be sure that you're clear whether or not you have the needed resistor in series with each LED in your circuit. Train detection, of course, is the foundation of signaling, and that's another big decision to contemplate. There's infrared detectors that you can mount in a hole between the rails or angled across the track. And then there's the resistance inductance method where you take the feeder wire to each block and detect it through the inductance in the coil there. The resistance method is a lot more realistic because prototype signals use track detection, but the disadvantage is you have to put resistance in a lot of the wheels. So signaling's bottom line is you have to find out where the trains are through some kind of track detection. You have to figure out the logical thing to do about it through some sort of electronic circuitry. And you have to light up the appropriate signals. So you have to have the LEDs in place and you have to have them wired up to all the electronic circuitry. And if you have those 3 things in place, you should have a working signal system. Sometimes detection is called sensors and the electronics is called signal logic. And there are all kinds of words for the appropriate signals. Aspect tends to mean which light is lit. And indication tends to mean what does that tell the locomotive engineer? In this case, a yellow light tells it to approach at medium speed. So now let's look at the question of how to accomplish the logic. And this is where it really gets complicated because the choices are so many. You can have simple microprocessor chips like the NCE mini panel, and Digitrax has equivalent panels, and you can program an Arduino to take care of your signaling needs. And I considered doing that. I think I could probably signal delta Y with an NCE mini panel, but I really wasn't sure that would be robust enough for future expansion. So I considered these other choices. LCC which is layout command control, has a relatively new set of products on the market that are designed specifically for setting up this signaling. And of course, they're the traditional methods of signal control. One of them is the Java Model Railroad Interface, JMRI, and the other one, of course, is Bruce Chubb's original Computer Model Railroad Interface, CMRI. And I'll show you a diagram of how these four choices differ in a second. This is the manual for Bruce Chubb's CMRI, which was a very famous series of articles that he did in the 1980s and 90s, actually, because computer model railroad control has gone through several iterations. This is a lot of information to read. It sets up what's called a star network. So in the red box, you have the master computer, which is a PC of some kind. And then it directly connects to a bunch of input-output boards with unique connectors. And then they connect, again with unique connectors, to signals, sensors, and switches that actually run the railroad. But in order for this to work, the master computer, the CMRI, has to have one huge computer program that keeps track of every single sensor, switch, and signal on the layout and reads the entire layout every half second or tenth of a second or however quickly you can do it. So this means that the computer is constantly reading the layout, and the layout's ability to respond depends on how quickly all of that input and output can take place. The other thing about this, of course, is the one huge computer program is customized to your layout, so you have to learn how to write computer programs and then maintain it. And every time you add a feature, you have to go in and reprogram your master computer program without having it crash. So I don't really want to have computer programming be my main hobby. So I was really looking for alternatives. Now, the JMRI system is an open source system that has a slightly different architecture called the master slave bus. And it uses the DCC command station and the track bus from that to send signals back and forth to and from both the locomotive decoders and stationary DCC decoders. Of course, the command station is also using the control bus to talk to the DCC throttles. This is slightly better because you can use the existing track bus to wire up your layout signaling system with the input-output stationary DCC decoders shown there. But it still involves the configuration of some pretty complicated signal logic tables in JMRI, and it requires that you have the JMRI computer hooked up to your command station, or else none of this works. It is, however, a good approach and being used by a lot of people. One of the drawbacks of it is that the track bus tends to get saturated with signals. One of the reasons for that is there are many redundant signals that are sent out to the loco decoders and the stationary decoders just to make sure everything is talking to everything else. The big advantage of LCC is that it uses something called a CAN bus to connect LCC circuit boards to each other back to a power supply, but doesn't require a computer. Essentially, these LCC circuit boards are tiny computers which can be programmed using JMRI, but once they're programmed, they work on their own. Now, this means that you can, for example, have your train layout have automatic signals working whenever you turn the layout on. And then when you have an operating session with a dispatcher who wants to control signals and dispatch trains, you can set up JMRI dispatcher panels and have dispatcher-controlled turnouts and things like that. So you can essentially have two modes for your layout, an operating session mode and a solo play with trains mode, where you just go down and run a train around the railroad without having to worry about a dispatcher. You'll still get the right signal indications. The final alternative, which also has some advantages, is to just install Arduinos every place you have a control point or a passing sighting. This means that every little town has its own self-controlled signal operation, and each town can talk to the adjacent town and pass signals back and forth. This has a lot of advantages in terms of being very modular. The only disadvantage to it really is that you need to master the process of programming the Arduinos and having them work well with each other. And again, that's just a headache that I wasn't interested in, considering that with the LCC CAN bus, you can do all that programming and aligning and testing just using the JMRI interface in a testing mode. And when you get it running, it's independent of a computer. Now, of course, the Arduino system is also independent of a computer because each Arduino is itself a little computer. But the programming is the part of it that made me wonder. So I decided to go ahead and try to learn as much as I could about LCC and see what it would be like to set up an initial LCC network for my Delta Y, and then over time expand it to the rest of my layout. If you've seen some of my previous clinics, you might remember this drawing where I complained loudly about how many of the devices in my control system for my layout were subject to firmware upgrades, and that this essentially made me an electronics technician rather than a model railroad hobbyist. You can see from the diagram that I envisioned the system as providing my operators with Bliss through wireless throttles connecting to wireless receivers, connecting to the DCC command station, working through circuit breakers to the track, the wheels picking up the current and sending it to the locomotive decoder, creating motion, light, and sound. Now, there is more than one way to achieve this Bliss, because not only can you have a regular wireless throttle, but you can also now buy a proto throttle, which has a different type of radio signal, much more prototypical levers and handles, but involves, two more sets of things with firmware upgrades. And of course, now with Y throttle and engine driver, you can have cell phone throttles using your local Wi-Fi to connect to your home computer to connect through the USB port to your DCC command station. So this situation seems pretty complex. This is without any signals, although it does give Bliss to a lot of operators. If we add signals to the mix, we have detectors in the track which go to the I/O boards. The I/O stands for input output, through wires to the LCC node. The LCC node then sends commands over the CAN bus, which is powered by the power supply, to a different LCC node, to another I/O board that lights the LED signals. That signal is then visible to the operator and gives even more Bliss than they had before. So you can see there's only two more firmware upgrades involved with those LCC nodes. And I don't know, I look at this and think it's not going to kill me. It's already bad enough, but how bad is a little bit more? Now, of course, if you're going to actually have a remote operating session, have your dispatcher located in a different city or your engineers, that's another can of worms that involves getting remote cell phone throttle and Zoom meeting access through the internet into your home router, and then through the Wi-Fi to the home computer that you have hooked up to your DCC command station and your signaling system. So it's just nothing but Bliss and more Bliss. One key thing that keeps me from being too afraid of this diagram, which otherwise would terrify me, is you notice there's a gap between the track and the detectors. And the key thing about either type of detecting, whether it's resistance detecting or infrared detecting, is that there is no electrical connection between the top circuit and the bottom circuit. The detectors are not touching the track and the DCC system through any kind of wire. They're just picking up the current from the locomotives without actually affecting it. So this means you really have a standalone independent signal system, and you don't have to worry about a short in one causing a problem in the other. So finally, the question is how to start. And of course, I recommend Dave Abley's new book highly, and various other MRR reference works, and there's a lot of them. I mean, Bruce Chubb had a long-running series of articles in Railroad Model Craftsman magazine, and there are many other places to find out about signals. There also is a groups.io group dedicated to layout command control, LCC, which has really benefited me in my learning curve because I can post questions there. And of course, I kind of demonstrated setting and refining goals for a starter project, in my case, going down to an initial Y with a total of 18 LEDs, which seems like something I should be able to do in the next few months. And as you saw my paperwork with labeling the signals, getting that done before trying to build any hardware. And I talked about buying new tools and building the skills to work on them. Well, the last two things to discuss is testing each component as you go, and don't forget to play with trains every chance you get. So this shouldn't feel like work. So we'll just talk about that. This is the starter setup that I've been playing with. The power supply is the black wall wart in the top there. The LCC signal node is the circuit board here. The test buttons are plugged into the signal node and allow you to do experiments with the configuration of the signal node. The computer with JMRI simply plugs in with a USB cable into this little circuit. And the computer, which is off the screen, has JMRI running. And of course, for that to talk to the network and to configure this board, the computer plugs into the USB to JMRI box, which is sitting right here. This is the other piece of the power supply. The black wall wart plugs into the little power point. This is just a close-up of the LCC signal board. Each of these terminals is involved in powering the LEDs. And the one in the end is the ground wire, and then the rest of the ports here are for the individual LEDs. You can see here I have the yellow light illuminated, which means that there's power between the ground here and the middle wire here. In this case, I was able to change it to the green wire. I also, you can see amid the mess here, I'm getting ready to try powering a switch machine, which will be a whole nother part of the process. I also found that they sell a volt amp meter so that you can actually monitor the performance of the CAN bus. And in this case, it's showing that I have something like 0.03 amps and 14 volts, which is fine. I also didn't mention, but all of these components connect together through standard Cat5 Ethernet cables. So it's very easy to do the wiring without a bunch of extra work. And of course, the last thing is to have fun with the layout. And here we have another very tense situation that could be improved with signaling in my version of Bayside Yard in Everett. And this is an example of some additional model railroaders having fun on a layout with an overhead light. And just to point out, there are other kinds of lighting you can do with this technology. Of course, there's no stopping this. Like all things in model railroad, once you get started, how do you stop? So in my case, I have a section of downtown Seattle on my layout with 3 at-grade highway crossings that all should have flashing lights and bells sounding. And I'm pretty sure that that'll be one of the next projects that I do once Delta Y is connected. I already mentioned lighting buildings. This is a picture of Seth Newman's layout in California. Look at all those building lights that he has on the loading doors and inside the windows. I think he has some building interiors that are lit. Really fun. Many thanks to Seth for his encouragement on this and the inexpensive signals that his company produces. So that's all. I hope you enjoyed this presentation, and good luck with your signaling projects.